let's do that. Let's construct that Taylor series for cosine. So what we want to do is we want to write a polynomial so that if I take the derivative of the polynomial, and we're going to center it at 0. So if I take the derivative of the polynomial at 0, I get the same thing as if I take the derivative of cosine at 0. And I want to do that for all orders of derivatives, not just the first derivative, but the second, third, fourth, and fifth, and so on. To do that, I'm going to use this formula. And I've got in a different video that I posted on the website, I have where this formula comes from. If you want to see where that formula comes from, feel free to watch that. But essentially what it says is each term of our power series we get by taking the derivative of some order. So the first term, actually, sorry, let's start with the 0th term. The 0th term, and I say 0th because we start at 0, is going to be the function itself. We're not going to take the derivative. Evaluated at 0 divided by, what's 0 factorial? 1 times x to the 0, which is 1, right? So the first term, or the 0th term, is just going to be the value of the function at 0. Then the first term, when we put 1 in for k, is going to be the first derivative evaluated at 0 divided by 1 factorial times x to the first. The 50th term is going to be the 50th derivative evaluated at 0 divided by 50 factorial times x to the 50th. So to get each term in this polynomial, in this Taylor series, we're going to use this formula here. Okay? To do that, the first thing we need to do is evaluate derivatives. So if I need to know what the 50th derivative is, I need to take the 50th derivative. Now, that sounds like a lot of derivatives, but when we have sine, cosine, even tangent to some extent, but those trigonometric functions, we're going to see a pattern in the derivatives. So let's go ahead and differentiate cosine a few times. Once we take the 4th derivative here, we get back to the original function, so the 5th derivative would be negative sine of x, and the 6th would be negative cosine of x, and the 7th would be sine of x, and the 8th would be cosine of x. And we just go through those 4 over and over again. So once we take the derivatives, since we're gonna center this at 0, and later on we'll look at how we can center this at some other point, because it wouldn't make sense to center it at 0 if I want to know what the sine of 100 is. Then I would probably center it at something else. But since we're going to center it at 0, we're going to evaluate each of these at 0. And we actually have to know the value of the function at 0 also. So what is f of 0? It's the cosine of 0, which is going to be 1. What is f prime of 0? Yep, that's going to be the sine of 0, actually negative sine of 0, but negative 0 is 0. How about the second derivative evaluated at 0? Negative 1. Third derivative? 0. Anytime we have a sine, we're going to get a 0 in there, right? Fourth derivative? 1. What's the pattern here? Patterns are great for this.
It's this cosine function.
Yeah, it's every pi over 2 of the cosine function, right? So 1, 0, negative 1, 0, 1, 0, positive 1. So every other term 0, and then every other term besides that is going to be positive 1, negative 1. So we could continue this pattern as long as we want here, and it's pretty easy to figure out what's going to happen next, right? What we've done here is we've figured out what's going to go right there in my power series. So anytime we have a 0, what's going to happen?
0.
It's going to be 0, right? So if we have 0, this is going to be 0 over something, and that term's just going to disappear. I'm going to do the first couple of 0 terms just to show you what's happening, but then we'll start skipping over those. So the first one here, if we're looking at the function itself, what k value are we using? Yeah, that's going to be when k equals 0. So when we're looking at the function itself, this is going to be when k equals 0. So when k equals 0, what's our term going to look like? So this right here that I have circled in green, that's going to be my 1. So we're going to get 1 over, what goes on the bottom? 0 factorial times x to the 0. Well, 0 factorial is 1. X to the 0 is 1. So what we end up with here is just 1. So our first term is going to be 1. And this makes sense because what is the value of cosine at 0? 1, right? So since the value of cosine at 0 is 1, then it would make sense for our first term to be 1. Because if I put 0 into this polynomial, every other term is going to drop out. Okay, now, how about the second one? The second one here, that's going to be when k equals 1. So we're going to have, what goes on top? 0 over 1 factorial times x to the first. Now all this stuff, the 1 factorial, the x to the first, those don't really matter because what's that going to be? That's just going to be a 0. Okay. Next one, we have k is going to be equal to 2 for this one. So what do we have on top for this one? What is the value of the second derivative at 0? -1. That's what we computed here. So we have -1 on top over 2 factorial times x squared. And so this is, if I write this a little more simply, it's going to be -x squared over 2 factorial. I could do this term here. This is going to be when k equals 3. But when I do that one, what's going to happen? It's going to be 0, right? It would be 0 over 3 factorial times x to the third. That one's going to drop out. So I'm not going to do that one. I'll skip it. So here we have k equals 4. So what are we going to have on top for this one? 1 over 4 factorial times x to the fourth. So if I want to write that a little more simply, it would be x to the fourth over 4 factorial. And again, this one's going to drop out. That's just going to be 0 when k equals 5. When k equals 6, this is going to be the last one I do because I think we'll see a pattern here. When k equals 6, what are we going to have on top? Over 6 factorial times x to the sixth. And so that would be the opposite of x to the sixth over 6 factorial. So what's the pattern here? Forget about this 0 term here. What's going on with the 0 term, the second term, the fourth term, the 6th term? What's the pattern? We're gonna put all these non-zero terms together and write out our polynomial. So we're going to have our p of x, and remember this is the polynomial that's going to approximate the cosine curve. That's going to equal 1 plus, minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. What would be next? Yay for patterns, right? Okay, and then that's going to continue forever. Since it's going to continue forever, if we want this to be an infinite process, we should probably write a general term. So for our general term, how do we show, or how are we going to account for this alternating pattern? Since we want to multiply by -1, what we're going to do is we're going to write it as -1 to the nth power. Now let's make sure that's going to do what we need. I'm actually using a different n here than I use for the k's here. I'm not going to call this the second term because it's a 0 term. So I'm going to ignore the 0 terms here when I'm using my n's. So if I put in, let's say we're going to make this first number here the 0 term. So if this one's the 0 term, that should be positive, right? I just want to check to make sure I've got it right. So if I put 0 in for n, is that going to give me a positive 1 or a -1? That's going to be a positive, which is what I want. And just to make sure, let's call this the first term. If I put a 1 in for n, is that going to be positive or negative? It's going to be negative, which is what I want. So this is going to give me the alternating pattern that I want. So this takes care of the sign, the positive or negative. Now I'm going to write the fraction. So I'm going to have x to some power. In the 0 term, what's the power on x? 0, right? In the first term, what's the power on x? in the second term, what's the power on x? In the third term, what's the power on x? So what do I multiply by x to get the power? I'm sorry, what do I multiply by the term number? It would be to the 2n, right? So if I put say 3 in for n, I would have negative 1 to the third power, that's going to be a negative, times x to the 2 times 3, which would be 6. So I would have negative x to the 6, which is what I need so far here. The last thing I have to take care of, though, is this in the bottom. So what am I going to have in the bottom? 2n factorial. Should I write it like that? What's wrong with that? That means 2 times n factorial, but we don't want that. We want the quantity 2n factorial. And that's going to be our general term. If we plug any number in for n, any counting number in for n, we're going to get that term in the sequence. And we just want to keep in mind that we started at 0 here. If I wanted to start at 1, that's fine. The only problem is I'd have to have a negative 1 to the n plus 1 here, or n minus 1, whichever way you want to go with it. This would have to be a 2n minus 2 here, and this would have to be a 2n minus 2 here, and that would get a little confusing, I think. So by starting at 0, it actually makes this easier. And again, this is infinite, so we'll throw that on the end. And this right here is what we call a Taylor polynomial.